Hi all, good evening. We are in the course session of week 6, the practice assignment session of the course contents covered in week 6. All of you get ready with your paper and then we can just start our session for today. Let's begin. If an input x of t is given to an LTI system that has impulse response h of t, what will be the output of the signal? What will be the output of the system? So we have a system. The impulse response of the system is h of t. We have an input that's given which is x of t. What is our output?
Convolution of input and response.
Exactly. So the output is the convolution of the input and impulse response. If an input with Fourier transform x of j omega is given to an LTI system which has a frequency response h of j omega, what is the Fourier transform of the output?
Multiplication of the frequency response.
Yes. So the output will be multiplication of the Fourier transforms. So if I have a system whose impulse response is h of t, the input is x of t. So what is our output? It's a convolution of x of t into h of t. Now we are taking Fourier transform of this entire system equation. So y of t's Fourier transform is capital Y of j omega. So y of j omega is equal to x of j omega into h of j omega. So the answer is B. The third question, consider an LTI system with impulse response h of t is e power minus 4t into u of t. The input that is given to the system is e power minus 4t into u of t. Basically, the input and impulse response are the same. Where u of t is the unit step signal. What will be the output of the system? So you are going to use the properties what we saw in question 1 and 2, and then you're going to find the answer for this question. X of t is e power minus 4t into u of t. H of t is e power minus 4t into u of t. What is y of t?
C1.
Okay, let us check the answer. Yes, you're right. So how did we get to the solution? Y of t is x of t convolved with h of t. In Fourier transform, it's the product of the Fourier transforms of the input and impulse response. Now, what is the Fourier transform of e power minus 4t into u of t? It is 1 divided by 4 plus j omega. So, when we had e power minus 80 into u of t, we had it as 1 divided by a plus j omega. So, this is the Fourier transform. So, now instead of a we have 4. So, it's 1 by 4 plus j omega into 1 by 4 plus j omega. Basically, it is 1 divided by 4 plus j omega the whole square. Now, how do we get, so how can we also write this as, if you see, if you have t into x of t, the Fourier transform of t into x of t is j into differentiation of x of j omega. So, if I differentiate 1 by 4 plus j omega, I will get 1 by 4 plus j omega the whole square. So, it is j into, if I differentiate this, you will get, so it's u by v, right? So, v into u dash minus u into v dash by v square. So, you will get j minus j square, so which is 1, and then 4 plus j omega the whole square. So, you get this. So, this we can also write it like this, j into d by d omega of 1 by 4 plus j omega. And then following this Fourier transform property, we get y of t is equal to t into e power minus 4t into u of t. So for this differentiation, it is u into v dash minus v into u dash by v square. Moving on to the next question. Now it's a similar question. Here h of t is e power minus 3t into u of t. Just proceed in the same way and see what is the answer.
D.
Okay. It is A. I think you missed the minus sign maybe.
Yes, ma'am.
Yeah. So for h of t, h of j omega is 1 by 3 plus j omega into x of j omega is 1 by 4 plus j omega. Now, how can I write this as? So there is a way to do it. So 1 by 4 plus j omega into 3 plus j omega. This I should be able to write like some a by 4 plus j omega plus b by 3 plus j omega. So this product of two terms, we should be able to write like sum of two terms. Okay, so we can write this as some a by 4 plus j omega plus b by 3 plus j omega. Now we have to solve this. So how we will solve it? So A into 3 plus j omega plus B into 4 plus j omega is equal to 1. So I'm just bringing this to the numerator, this to the numerator, then we can equate it to 1. Now we have these two, okay. We will substitute different values of omega and we will find A and B. For example, if I am going to put omega as, say, how can I write? So if you put omega as 0, first we will get 3a plus 4b equal to 1. Second expression, if I am putting omega as 1, so I will get 3a plus ja plus 4b plus jb equal to 1. Here if you see, j into a plus b term, right? J into a plus b term can be equated to 0 because here you just have a real number. You don't have any imaginary number, right? So 3a plus 4b should be equal to 1, which we got previously. Second expression is a plus b is equal to 0. So we get a as minus b. So a and b are just inverse of each other. Okay. So from this I am getting a is equal to minus b. Then I will substitute it in this equation and then I will be solving it. So if I solve, I will get a as minus 1 and b as 1. So now we have to find the inverse Fourier transform for the same thing. Sorry. So for this it is e power minus 3t minus, for this it is e power minus 4t into u of t. So this product we should be equating it to sum of two fractions. Then we have to find a and b and then we have to write it and then do the inverse Fourier transform. So the answer is a, e power minus 3t minus e power minus 4t into u of t. Moving on to the next question. We have a LTI system whose impulse response is h of t is equal to e power t cos t into u of t, where u of t is the unit step function. What kind of a system is this? Is it a causal system? Is it a stable system? Or which of these combinations? Our impulse response is e power t cos t u of t. So based on our impulse response, we should be able to find what type of a system it is. Can you guys try this?
Stable but not causal.
Okay. I'm just waiting for one more minute. So, to know the stability and causality of a system based on the impulse response. A system with impulse response h of t is stable if integral minus infinity to infinity h mod of h of tau d tau is less than infinity. So, if I take the integral of the mod of the impulse response, if it is less than infinity, then the system is a stable system. Now the system is causal if h of t is equal to 0 for t less than 0. That is, for negative values of t, h of t is 0. It does not exist for negative values of t. It only exists for 0 and positive values of t. Then the system is causal. So these are the two conditions to check stability and causality of the system. Now we are checking for the system h of t as e power t cos t into u of t. Okay. First, it has u of t. So u of t means how does u of t look? So for t less than 0, it is 0 and it exists only for t greater than 0, right? This is u of t. So h of t has u of t term, which means h of t is 0 for t less than 0. So the system is directly a causal system. Whenever you get u of t, you can almost tell that the system is a causal system, like this. If it comes like e power t cos t into u of t, right? We know that u of t is a causal thing, causal signal. So if you have h of t, u of t in the h of t expression, then we can tell that the system is a causal system. Okay. Now we are going to check for stability. How do we check stability? Integral minus infinity to infinity mod of h of tau d tau should be lesser than infinity. Okay. So we have e power t cos t into u of t. Since I have u of t, my integral limit will go from 0 to infinity. So integral 0 to infinity e power t cos t dt. So this is in the form of this integral u into dv. So how do you solve integral u into dv? uv minus integral v into du. What is our u? What is our v? U is e power t. dv is cos t dt. Now we need, we have u, we have dv, so we need v, right? V and du. So u is e power t. So what is du? Again, if you differentiate e power t, I am going to get e power t dt only. dv is cos t. So if I integrate cos t, I will get sin t. So with this, I am going to write this integral as e power t into sin t. The limits are from 0 to infinity, right? Minus integral v into du, sin t into e power t dt. If you see this term is going to go tend to infinity. So this integral evaluates to infinity, it tends to infinity. So this system is a unstable system. We don't get this mod to be lesser than infinity. We don't get this. This system is an unstable system, but it is a causal system. So the answer is causal but not stable. Is the idea clear? Like how to find the causality and stability of systems? Is it okay, guys?
Yes, ma'am. Yes, ma'am.
Now you have h of t is e power minus t cos t into u of t. Now can you tell what kind of a system is this?
causal and stable.
Okay, I'm waiting for some more time. Yes, so your answer is right. So it's almost the similar argument as the previous question. We have h of t is e power minus t cos t into u of t. So we have u of t. So it is 0 for t less than 0. So h of t is a causal. So since h of t has e power minus t cos t u of t, the system is a causal system. Now we are going to do the condition for stability. Integral minus infinity to infinity mod of h of tau d tau. Same u into dv formula we have to apply. So it is uv minus integral v into du. So instead of e power t, we have e power minus t. So du will be minus e power minus t. dv is going to be the same thing. So if I solve this integration, I am going to get e power minus t into sine of t. Limits are from 0 to infinity plus integral 0 to infinity sine t into e power minus t into dt. Now we have e power minus t. So when t is tending to infinity, this exponent is going to die out. This is going to tend to 0. Correct? So this is going to evaluate to a value which is lesser than infinity. So the system is a stable system. So the system is a causal and stable system. Moving on to the next question. Which of these systems is invertible?
Option C.
Okay, right. So we are checking the invertibility of a system based on the impulse response. A system with impulse response h of t is invertible if we are able to find another system which has an impulse response hi of t such that we have the output as x of t. So basically we have input x of t, system is h of t, output is y of t. Now we should be able to find a system to invert this y of t back to x of t. So that system, whatever we are finding, this black box should follow this criteria. H of t convoluted with hi of t should be del of t. only if this condition is satisfied, we will be getting x of t in the output of the second system. The main quick check what we can do is, to be invertible, the input output mapping has to be only 1 to 1. That is, the input should be mapped only to one output. Same way, the output should be able to be mapped only to the same input. Basically, the relation between input and output should be 1 to 1 relation. So for our question, if you see y of t as x square of t, okay, if x of t is plus x of t or x of t is minus x of t, y of t is going to be the same thing, right? Y of t is still going to be positive. So, if I have an output y of t, I have some output. So, will I map it to x of t or x of minus t? Which I will map to? There comes a confusion, right? So, we cannot map this directly to one of the inputs. So, this is not an invertible system. Same thing holds for sine of x of t. For multiple values of x of t, we will be getting the same output, right? For multiple values of x of t, sine is going to have the same value. So again, this is not an invertible system because it does not have a one-to-one mapping. Same with the last also, x of t square. So if t is positive or negative, x of only positive value is taken. Again, you cannot map it to one-to-one. You don't have a one-to-one relation. So this is also not invertible. So the answer is C. Y of t is e power x of t. If you check for this system, it's always a one-to-one mapping. So this system is an invertible system. Moving on to the next question. For an LTI system with input x of t is e power minus 2t into u of t. What is the output y of t if the input and output are related by this differential equation? So if you have this differential equation, we know what is x of t. We have to find what is y of t. How do we do it?
I think this needs some calculations.
Here. So maybe I'll just quickly go through the solution so that you guys can try it. Basically, what we are doing is we are taking the Fourier transform. Okay. So if I take the Fourier transform of this differential equation, dy by dt means it is j omega into y of j omega plus phi into y of j omega is equal to 3 into x of j omega. We have to find y, right? So what we will do is we will keep y of j omega on one side. Okay, so y of j omega into phi plus j omega will be equal to 3. One second. So 3 into for x of t it is given as e power minus 2t into u of t, right? So that I will write it here. So x of j omega is 1 divided by a plus j omega, 2 plus j omega. Now this y of j omega will now be equal to 3 divided by 5 plus j omega into 2 plus j omega. So this goes here. So 5 plus j omega into 2 plus j omega. This is our y of j omega. Now, so there is a very simple way to do it. So as I told you, this product, so 5 plus j omega into 2 plus j omega is now equal to a by 5 plus j omega plus b by 2 plus j omega. Right? This product we should be able to write it like sum of two fractions. Now, what can we do with this? So 2a, sorry. So 2 plus j omega into a plus 5 plus j omega into b is now equal to 3, right? Now, if I put omega is equal to 1, what I will get? A plus b, that is 2a plus 5b plus j into a plus b is equal to 3, right? So if I put omega equal to 1, I will get this expression. So here if you see on the right hand side, we don't have an imaginary part. So a plus b is equal to 0. So a is equal to minus b directly. So if a is equal to minus b, I will substitute in this expression. So 2a plus 5b is equal to 3 and a is equal to minus b. So directly I can find a and b. So I will get a as minus 1 and b as 1. So this I will be writing as 1 by 2 plus j omega minus 1 by 5 plus j omega. Now to find inverse Fourier transform, y of t will be equal to e power minus 2t minus e power minus 5t into u of t. So from this fraction, product of two fractions going to this sum of two fractions, if you do it in this way, it is like a bit easier. You can substitute some value for omega and then equate on both sides and you can find a and b quickly. Now it's like it needs a bit more calculations, but you guys can attempt the question at least. Like you can proceed till half and then we can discuss how to get the solution. Okay. So x of t is like this. So it is 2 for 0 less than or equal to t less than or equal to 2 and it's 0 otherwise. H of t is x of alpha t where alpha is greater than 1. What is y of t? Basically this is the impulse response and this is the input that is given to the system. So what is x of t? X of t is very clear to us. So it is from 0 to 2 to this is x of t. What is h of t? H of t is x of alpha t where alpha is greater than 1. What if alpha is 2? What will happen? If alpha is 2, x of 2t means this time compression, right? So here I will be getting so t by alpha. So basically I'll be getting 2 by alpha. This is 2. So this is our h of t. So is this clear, guys? So h of t is given as x of alpha t. And alpha is greater than 1. If alpha is greater than 1, basically we are doing time compression. So if alpha is 2, we would have divided it by 2, right? The entire time scale we would have divided by 2. So basically if it is alpha, we will divide by alpha. So 0 to 2 by alpha and then y-axis we have 2, this is our h of t. Now you have to determine what is y of t. How do we do it?
Pardon, ma'am?
So we have to find what is y of t. We have x of t, the input, we have impulse response h of t. We are finding what is the output y of t. So what is our y of t? X of t convolved with h of t. So directly you can proceed to do this convolution and then apply the convolution formula and we can get the answer.
After taking this frequency domain, and in frequency domain we get the delta functions. So from that we can write it now.
Yes, yes, yes. You can take it to frequency domain. That is, you will be differentiating this, right? You can differentiate this, you can differentiate this, and then you can go to the frequency domain transform and do. Here R of t is our unit ramp. So how do we write R of t? R of t is t into u of t. So wherever you have t into u of t, it is basically R of t. I just try to give you the steps in the way like how I have tried to solve it. Okay, so how it is I have done is, we know what is x of t, so it is still 2, the magnitude is 2. H of t also we know, so the in time axis it is 2 by alpha, right? How can I write this as in terms of unit step? What is u of t? U of t is something like this. What is u of t minus 2? U of t minus 2 is from 2 to infinity, right? So this is u of t minus 2. So u of t minus u of t minus 2, if I do, what I will get? I'll get non-zero portion only till this 2. Correct? So u of t minus u of t minus 2. So I will be getting x of t. And in y-axis, the amplitude is scaled by 2 units. So it is 2 into u of t minus u of t minus 2. Okay. Same way, I am writing h of t. So 2 into u of t minus u of t minus 2 by alpha. Instead of 2 here, we have 2 by alpha here. So it's t minus 2 by alpha. And then I have just done the normal convolution. So h of tau, x of t minus tau, d tau. Actual direct convolution formula. And then h of tau we can write as 2 into u of tau minus u of t, tau minus 2 by alpha. And then x of t minus tau you have to write. And then based on u of t, we have to change the limit. So here if you see in all the 4 places, we just have product of 2 unit steps. Okay. So with this you have to find what will be the limits of integration. And then inside we just have 1. So we have to integrate this and then we will get t into u of t minus this, you will get t minus 2 by alpha into u of t minus 2 by alpha. Same way for this. So we will get 4 terms. T into u of t, we are writing it as unit ramp. So the answer is 4 into r of t minus 4 into r of t minus 2 minus 4 into r of t minus 2 by alpha plus 4 into r of t minus of 2 plus 2 by alpha. So the trick followed here is trying to express x of t and h of t in terms of unit step functions, and then using the usual convolution formula, but the integration is very simple, like you just have product of unit steps and then we could try to find the limits based on the unit steps and then we can arrive at the solution. Now for equation 1, which value of alpha does exhibit only 3 discontinuities for dy of t by dt? That is, we have found what is y of t, right? So y of t is this. If I find dy by dt, if I differentiate this, how many discontinuities? That is, I should have 3 discontinuities. If I should have only 3 discontinuities, what will be my value of alpha? That is, this is y of t. If I find dy of t by dt, it should have only 3 discontinuities. If we should have only 3 discontinuities, what should be my value of alpha? You can do this in multiple ways. First, you try to differentiate this expression and then try to get the expression. And then you could try different values of alpha and find for what value of alpha you are getting 3 discontinuities, only 3 discontinuities. I'll just try to give the idea how to solve it. Okay? So we have y of t that's given. So y of t is 4 into r of t minus 4 into r of t minus 2. So 4 into r of t means what? It's something like this. 4 into r of t minus 2 means from 2 it is like this. Same way we have 4 into r of t minus 2 by f and everything. So first for 0 to 2, if I subtract these two, what I will get? So here it is 0. So up till 2 it is direct line. So up till 2 it is direct line. And then same way from this up till we have 2 by alpha, right? So this, if I subtract this, I'm going to get some line like this. And then here it is negative sign, here it is positive sign. So this is going to drop something like this. Now, for this thing, first what I'm trying is alpha is equal to 1 I'm putting. Okay. If alpha is equal to 1, this we don't get this straight line at all. So if alpha is equal to 1, both these points are the same, right? So you get something like this, some triangular function. And then if I find dy by dt of that, so up till 2 you have a straight line here, and then at 2 you don't have anything, so it's something like that, nothing. And then again from 2 to 4 you have a decreasing slope, so it is something like this. At this point it's something like this. So if you differentiate this y of t, this triangular function, I'm going to get some pulse like this. And how many discontinuities do we have here? We have a discontinuity at t equal to 0. We have a discontinuity at t equal to 2 and another discontinuity at t equal to 4. So the answer is alpha equal to 1. So what I did, I first wrote what is y of t, then I tried to substitute different values of alpha. So for this question, for alpha equal to 1 itself, we got some y of t like this, and then when I differentiated, I got 3 discontinuities. So the answer is option A. Now we have x of t as some subtraction of two unit step signals, and h of t is e power minus 3t into u of t. Now what is our y of t? Can you guys attempt this question?
I think it's option D.
Okay, I'll just wait for a few more minutes. So the answer is option B. Here I have done like the straightforward convolution, but you could very well try to do it by taking Fourier transform. Okay, so here what I've done is proper convolution formula, and then I have I'll get two terms. So u of t minus 3 into convolved with e power minus 3 t u of t, and another term is u of t minus 5 convolved with e power minus 3 t u of t. So, and then based on the product of the unit steps, our limits will change, and then if we solve, we can get the answer. But the option is B. Now we have two systems. We have two impulse responses, H1 and H2. Can you guys tell which of the impulse response indicate a stable system? We already saw that this is a stable system. What you guys have to do is find whether H1 is stable or not. Based on that, we could choose the option.
Both H1 and H2 are stable only, ma'am.
Okay. So how did you guys check the condition for stability? Integral minus infinity to infinity mod of h of tau d tau should be lesser than infinity, right? If this condition is satisfied, our system is a stable system. So for H2, we already saw that it is a stable system. That is, how will H2 look like? It is e power minus t. So the outer envelope is e power minus t. And then in this we have a cos of 2t embedded in it. So we get something like this. So it's a falling or a decaying exponential. So it's something like this. Or t, when t tends to infinity, this is going to tend to 0. So this is a stable system. The other one, H1, is e power minus 1 minus 2j into t into u of t. So we are finding the mod and then integrating it from minus infinity to infinity. When I am finding the mod, I am getting it as e power minus t into u of t. So if I am integrating it, since I have u of t, my limit is 0 to infinity. So 0 to infinity e power minus t, it is tending to 1, which is lesser than infinity. So H1 is also a stable system. So H1 and H2 both are stable systems. Okay. So we are in the last question for today. Comment on the causality and stability for a system with impulse response as follows.
I think it's option B.
Okay. Let us wait for 2 more minutes. Actually, the answer is it's neither
Option
causal.
C.
No, it is not causal, it is not stable as well. So first let us see why it is not causal, okay? So if I see the second term, it has u of t. So, okay, so h of t is not 0 for t less than 0. So since I have this term, okay, let us maybe directly see the plot. So we are plotting h of t, okay? This is the plot for 2 e power minus t. So when t is tending to infinity, 2 e power minus t will tend to 0. And when t is tending to negative infinity, it is going to tend to infinity. Okay. The second term is e power t minus 100 by 100 into u of t. So this, if you see it, since you have u of t, it is going to be non-zero only from t greater than or equal to 0. So this is going to be the second term. So it is subtraction of two terms. H of t is subtraction of these two terms. So I will get something like this, something in the negative side also and something in the positive side also. So if you see this h of t exists for t less than 0 also. So you have some things for t less than 0 also. So this system is directly not a causal system. Same way, for t less than minus, for t tending to minus infinity, the system tends to infinity. So this system is an unstable system. H of t is basically diverging. So the system is not a stable system and it is not a causal system as well. I have written a code in MATLAB to check the causality and stability. Basically, the condition what we have for causality and stability, I have written in the in MATLAB form. Now, if we okay, I'll just go to MATLAB and show one example. So I've already written the function in MATLAB. Okay, so here how am I checking for causality means if I have something for t less than 0. If h of t exists for t less than 0, then I will tell that the system is not a causal system. Okay. Same way, integral minus infinity to infinity, if mod of the impulse response, if it is lesser than infinity, then I will tell it is stable. Basically, if it is equal to infinity, I will tell it is unstable. So what we are going to do is, I will share this PPT for you, you guys. You can have this function and you can test it when you're free. So here I am showing you one example. Enter the impulse response of a system. Okay. So maybe we saw e power minus t cos t u of t, right? Maybe we can enter that. So e power minus t, okay, t is our variable. So e power minus t cos t into to write unit step function. Here it is called heavy side. Okay, so heavy side of t. So we are checking the stability and causality for e power minus t into cos of t into u of t. Okay. We saw in our example that this system is a causal system and this is a stable system as well. So we are getting the answer, the system is causal, the system is stable. So like this in MATLAB, like for the past few sessions, I have been showing you different operations we can do in MATLAB. So this is one example that we can also test the causality and stability of systems as well. So if you write the conditions to check for the respective ones, for any impulse response, we can see whether the system is causal and stable. So this is the power of MATLAB or even Octave. Both are just almost one and the same. This code, as like in a PPT format, it will be shared with you in the NPTEL website. So you can copy and paste this function in Octave or MATLAB, and then you can try for different impulse responses. You will be getting the answer. Is it okay, guys?
Okay, ma'am.
Okay. I think if is anybody having any doubts?
No, ma'am.
Then we can end the session for today. Thank you all.